Let's explore the following series. Suppose that we have the series from n equals 0 to infinity, negative 1 to the power n, 4 divided by 2n plus 1. And suppose that we want to approximate this value up to an error of 0.00001. In order to do this, first we need to check for the convergence of the series. We need to check if the series is convergent. And then we need to find the approximation. In order to do this, first we're going to find if the series converges or not by using the alternating test. Notice that the sequence that is associated with the series is negative 1 to the power n times 4 divided by 2n plus 1. Now this is an alternating series, which means that we are going to use the alternating test. In order to use the alternating test, really what we have to do is just to find the limit as n tends to infinity of the absolute value of the sequence. In this case, this is just finding the limit as n tends to infinity of the absolute value of negative 1 to the power n, 4 divided by 2n plus 1. So in this case, the absolute value is going to get rid of the negative 1 to the power n. So we just end up with the limit as n tends to infinity of 4 divided by 2n plus 1. Now notice that the top part of this fraction stays constant while the bottom part changes. So this actually goes to 0. Now we have that since this limit is equal to 0, the alternating test tells us that the series is going to converge. In other words, by the alternating test, we have that the sum where we're looking for n equals 0 to infinity, negative 1 to the power n divided by 2n plus 1 is convergent. So that's the first part. We now know that there is a number out of this sum, which we can call S, their existent number. And now what we want to do is we need to approximate that number within the prescribed error, which is this one in this case. In other words, now we want to find a partial sum. What we're looking for is a value for n. We want to find this value for n such that the error between the approximation and the actual value is smaller than 0.0001. So we want this, this error, sorry, I was missing 1 0. We want this error to be within 0.00001. In other words, what we want to do is we want to find an error that is smaller than this number, and because we're dealing with an alternating series, we know that the error is going to be bounded by the nth term or the nth plus 1 term of my sequence. In other words, we know that the error, and this is a general result, which is S minus Sn, is always bounded by the absolute value of the a n plus 1 term. So in this case, what we have is that the absolute value of a sub n plus 1 is equal to the absolute value of, I just have to plug n plus 1, capital N plus 1, instead of n in my sequence. So that will give me 2n plus 1 plus 1. Again, notice that the only thing we're doing is we're taking the original sequence that is right here, and we are setting n, little n, to be capital N plus 1. So whenever we do this, this is the expression that we arrive with, and then this gives me 4 divided by 2n plus 3. So if we simplify that expression, that's 4 divided 2n plus 3. And what we want is we want to find n such that this is smaller than 0.00001. We want to find a large n for which this error is going to be smaller than the threshold we have. That means that we're looking for solving this inequality. We want to find an n such that this is smaller than the number I want the error that I'm looking for. So this will give me 4 divided by 0.00001 smaller than 2n plus 3. And then I can solve for n, and this will give me 4 divided by 0.00001 minus 3, and then I just divide everything by 2. So any n, any capital N that is bigger than this number is going to give me the desired result. So in other words, if we simplify this a little bit more, what we end up with is 2 divided by 0.00001 minus 3 halves should be smaller than n. So now I can grab a calculator and compute this number, and that will give me the estimate for what is the least amount of terms that I have to add in order to get this desired error. So I'll just go to my calculator and compute what is this number. So it was 2 divided by 0.00001 minus 3 over 2. So then the minimum number of terms that I need to add is given by 199,998.5. In other words, basically if I add 200,000 terms, that will give me the desired error that I'm looking for. In other words, let me write down over here. We have that the number I was looking for was 199,998.5. So any n that is bigger than this estimate is going to give me the desired error I was looking for. In other words, a good estimation or approximation for the original series is going to be given by S sub, let me do 200,000. In other words, this will be the sum n equals 0 to 200,000 of -1 to the power n 4 divided by 2n plus 1. This is going to give me then a number that is very close to the original series, to the infinite series I was looking for at the beginning. It's not going to be the exact value, but it's going to be a very close value. So let me use my calculator to find this number. So now I want to do the sum, the partial sum of the expression that I have in here, -1 to the power n, 4 divided by 2n plus 1. And then we want to sum this from n equals 0 to 200,000. So this is the advantage because a calculator can do this pretty easily for me. So in here we are adding the first 200,000 terms, and we see that the approximation, if I want I can find more digits of this, is going to be 3.14, 15, 97, 65, and so on. So let me write down that approximation in here. That would be then given by this. So we have that the sum we were looking for basically is going to be approximated by 3.14, 15, 92, and other terms in here. Again, notice that this is going to be within 0.00001 of the actual value. That means that I know that this is accurate up to this point. And this looks familiar. This sum looks familiar. This looks like the original sum could be maybe close to pi, which is very interesting. So what we have in here is we show that the original sum, the original series was convergent. We also found the number of terms that I needed to add in order to have an error of 0.00001. And I just grab a calculator in order to find that approximation, and that's the approximation we got in here.